In the beginning, there was energy, vibrating, oscillating, and shifting through every atom of the cosmos. But beneath the warmth of a sunbeam or the hum of a machine lies a mystery far deeper than heat or motion. Welcome to Quantum Thermodynamics, where the rules of energy, entropy, and information no longer obey classical intuition. Here, heat can tunnel, entropy can reverse, and information itself becomes the fuel of reality. Today, we explore the laws that govern the very fabric of energy, from the steam engines of the 19th century to the entangled particles of the quantum future. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. Our story begins in the 1800s with three visionaries: Rudolf Clausius, William Thomson, Lord Kelvin, and Ludwig Boltzmann. They sought to understand one of nature's most profound questions. Why does heat flow from hot to cold, and never the reverse? Clausius defined the concept of entropy, a measure of disorder. Boltzmann connected it to probability, showing that entropy rises because disorder is simply more likely. Together, they laid the foundation of thermodynamics, the science of energy transformation. But their world was classical, predictable, deterministic, and smooth. Atoms were billiard balls, not probability clouds. Heat was continuous, not quantized. No one yet imagined that the very laws of heat and work would one day collide with the strange, probabilistic world of quantum mechanics. In 1900, Max Planck faced a paradox. Why did blackbody radiation not produce infinite energy at high frequencies? His radical solution: energy comes in discrete packets, or quanta. One idea shattered centuries of classical physics. A few years later, Albert Einstein took it further. Light, he proposed, wasn't a wave or a particle. It was both. Each photon carried energy proportional to its frequency. The world was no longer continuous. It was quantized. This realization reshaped not only physics, but the very concept of energy flow. If energy exists in quantized chunks, then heat, the random motion of particles, must also follow quantum rules. In this moment, the seeds of quantum thermodynamics were planted, though it would take a century before the field would bloom. In the early 20th century, John von Neumann introduced a new way to describe systems statistically through density matrices. He defined quantum entropy, a measure of uncertainty in a quantum system, bridging thermodynamics with information theory long before computers existed. Around the same time, Erwin Schrödinger gave us his wave equation, describing how quantum systems evolve, not deterministically, but probabilistically. In this new view, even heat and work could fluctuate. At the quantum scale, the line between energy and information blurred. Quantum mechanics was never just about particles. It was about possibilities. And in a universe governed by probabilities, entropy was no longer a measure of ignorance. It was a measure of reality itself. Fast forward to 1961. Physicist Rolf Landauer, working at IBM, proposed something revolutionary. Information is physical. Every bit of information stored or erased in a computer requires a minimum amount of energy. kTln2 joules, to be precise. That tiny cost connects computation to thermodynamics. Landauer's insight transformed how we see energy, not as just mechanical or electrical, but informational. Later, Charles Bennett showed that reversible computing could, in theory, eliminate this energy cost, if we could avoid erasure. And in the 21st century, quantum physicists extended this principle to qubits, where entanglement, coherence, and measurement determine the thermodynamic cost of knowing reality. The message was clear: the act of observation itself carries an energetic price. Information is the new entropy. Today, the once theoretical field of quantum thermodynamics is becoming experimental reality. In 2016, researchers such as Massimiliano Esposito and Sebastian Deffner explored the limits of energy transfer in quantum systems, revealing that even a single atom can function as a quantum heat engine. Unlike classical engines, these devices exploit superposition and entanglement to approach the ultimate limits of efficiency, the quantum Carnot cycle. At the University of Oxford and ETH Zurich, teams have trapped ions and photons to study how heat flows when coherence, not chaos, dominates. Their findings blur the boundary between mechanics and information. Can we extract work from entanglement? Can quantum coherence itself be a thermodynamic resource? These are not questions of philosophy anymore. They're questions of engineering. The future of clean energy may lie not in combustion or fusion, but in mastering energy at the quantum scale. Entropy defines the arrow of time. It tells us why eggs don't unscramble, why stars cool, why the universe expands toward disorder. But what if time's arrow itself is quantum? Recent studies by Giulio Ciribella, Czeslaw Bruckner, and others suggest that at the quantum level, causality, the very order of cause and effect, may become indefinite. In these systems, entropy may fluctuate backward, at least locally and momentarily. Quantum thermodynamics suggests that time, like energy, may not be absolute, but emergent. It arises from information flow, from the exchange of energy between observer and observed. In this sense, every act of measurement is a creation of time itself, a crystallization of probability into history. As we stand at the dawn of the quantum era, the boundaries between energy, information, and consciousness are fading. Quantum batteries promise near-zero loss energy storage. Quantum computers redefine efficiency, operating at the thermodynamic limits of logic. And emerging theories in quantum biology suggest that living systems may already exploit these same principles for survival. The universe is not merely a machine, it is an information processor. Energy, entropy, and information are not separate forces, but three expressions of the same cosmic code. And as we decode that code, we come closer to understanding the ultimate law of the universe. Knowledge itself is energy, and every bit we learn shapes the fabric of reality. This is quantum thermodynamics, the science of how the universe computes itself. If you found this exploration enlightening, like, subscribe, and share this video. Leave me a comment. Let me know what you think about quantum thermodynamics and how it's shaping our future. Join us next time as we uncover the mysteries that bridge physics, consciousness, and the quantum frontier.